Hello and welcome back. So far we have understood, the how gradient descent algorithm works and notational part and why derivative is actually giving you the slope, right? Let us try to understand how to make the gradient descent algorithm converge, not to diverge. Or let us try to understand what is convergence and what is divergence, because when we are using the stochastic gradient descent algorithm from the scikit-learn, we need to understand these concepts and need to play accordingly to find the best hyperparameters like learning rate. So if you look at the algorithm, right, how it is exactly finding the best thetas at the best fit line, right, that's how it is working. Actually, it is started with some random theta and then it went to the best fit place, right? So let us try to understand how exactly that convergence happens, right? Slowly moving towards the global minimum. So in the initial understanding of gradient descent, I explained that when you don't have the slope, it is going to go off the track, right? Your theta may have started with 6 and it may go all the way back to minus 10 or something like that, right? So if your alpha is too small, right? Suppose that your current alpha is 0.5, 5.4, right? Your current theta is 5.4, and if your alpha is 0.001, right? If your alpha is 0.01, what happens? 0.01 into 001 into 16. It is going to be like maybe 5.4 minus. It's going to be like 0.016, right? Then the reduction in theta is going to be very less. That means from 5.4 it may move a little less, right? A little only, like a minute number. So if your alpha is too small, what happens? Instead of making a step from 6 to 5.5 and 5.5 to 4.5, 4.4, it will move from 6 to 5.9, maybe 5.98, maybe 5.99, and then 5.98, 5.97, 5.96. It is going to take more iterations or more steps. At every time you are calculating slope, you are actually taking new theta and then calculating, right? So you need to calculate theta and then again calculate the slope, again calculate theta, again calculate the slope. So every iteration you are making less move, so your alpha should be chosen appropriately. The learning rate should be chosen appropriately. If it is chosen appropriately, like 0.1, right? Here previously we have taken 0.1, 0.1 as the alpha, right? If you chose 0.1 as the alpha, right, it actually converged from 5.4 to 4.4. So it will have quickly converged to the global minimum. But when it reaches here, right, the slope is kind of getting close to zero. Or here it is almost zero, but not zero, right? So here it is close to zero, and here it is almost zero, right? So when it is close to zero, and alpha is already 0.1, right? 0.1. Your alpha is already small, right? 0.1 into, here slope was 16, so it was like that. But when it reaches here, right, that's also going to be very close to 0, maybe 0.24 or something like that. This becomes 0.0024. So the number will not reduce much. Maybe it is 3 here, right? 3 will not reduce much. So when the convergence happens, the convergence will be faster till here, and from here till here it is going to be slow. If your alpha is not chosen properly, right, if your alpha, the learning rate is not chosen properly, the convergence will become slow, and in the iterations you have given, like maybe 300 iterations or 400 iterations, the theta may reach only till here because of alpha is being too small. That means the cost is going to be still high. The model is not the best fit model or the high bias model it's going to be, right? So to make the model best fit, you may have to increase this 400 iterations to maybe 1000 or 10,000, we don't know, right? Or instead of increasing the iterations, it is always best to choose the alpha properly, maybe increase the alpha. When you chose 0.001, it took 10,000 iterations. If you choose 0.1, it may finish in 300 iterations. When you are increasing one number and reducing the iterations, that means you are saving lots of resources, memory and processing and all that stuff, right? So playing with learning rate and finishing the convergence, right? If the theta, the theta reaches here, right, the slope is going to be 0. That means theta is equal to theta minus 0 into, alpha into 0 is equal to theta. Again, theta is equal to theta minus alpha into 0. Once it reaches 0, right, the slope 0, it will stay there. That means it will come to the best fit line and it will stay there. So when your alpha, the learning rate, is properly chosen, the convergence becomes faster. In other words, if you choose alpha a big number, suppose that if your alpha is 1, right, theta is equal to theta minus 1 into slope, right? What is slope? 16. So here it is 16. What is theta? Theta is 6. 6 minus 16 is minus 10. Instead of converging, what happened? From here, it actually jumped all the way. Give me 1 second. It actually jumped all the way. Minus 10 is somewhere here, right? Somewhere here it jumped, minus 10. Maybe for explanation purposes, let us take minus 10 somewhere here, right? So minus 10 is here, right? Slope here is 16, so here it's going to be more, right? Maybe 26 or something. In the next epoch, what will happen? Theta is equal to, what is theta here? Minus 10 minus, the slope is going to be negative on this side, because this side, the theta and j of theta is going to be more than j of theta plus h. So it's going to be negative here. So you put 9 minus 96, 26 here, or maybe 28. Okay? Or maybe, it's going to be plus 18. So from here it's going to go to 18 here. Again it will go up. Again it will go up. So it will start here and go there, go there, go there. Like that, it is going to diverge. It will never reach the global minimum. So the alpha should be chosen properly. The alpha is too big, it is going to diverge. The alpha is too small, it is not going to converge properly, and you will get in both ways you will get biased model, high biased model. If your alpha is properly chosen, the model will converge properly to the global minimum. So how to find it? In our code example, we will see how to find it. Right? By looking at the error and playing with this alpha, you will understand what is happening, and appropriately you can choose the appropriate alpha. We will take help from GridSearch CV also to choose the alpha. So that is how the explanation goes about convergence and divergence. The same points were written here. If the step size is too small, the alpha is too small, convergence takes too long, and you may have to run more iterations. If it is too big, it may diverge. So by looking at the error, you can make the decision whether to reduce the alpha or increase the alpha. This is called as hyperparameter tuning. Okay, the learning rate you adjust and make the model converge faster towards the global. So that is about convergence and divergence. And on the if the random theta, initially it starts with random theta, I said, or a line somewhere here or here. Your data is in between, right? Either this side or this side, the line is chosen, it will converge to the global minima only. Right? Why? Because if you look at the formula, theta is equal to theta minus alpha into derivative of cost function. On the right side of your global minimal theta, the derivative is going to be positive, because theta is here, theta plus h is here. So j of theta is going to be below j of theta plus h. The derivative formula is j of theta plus h minus j of theta by h, right? So it's going to be positive. But here on the left side, j of theta is going to be here, j of theta plus h is going to be here somewhere forward. Right? So j of theta is going to be higher compared to j of theta plus h, right? So let me take a screenshot and explain. On the left side, the slope is going to be negative. Okay, so let me take a screenshot and explain. So here, if you look at theta and theta plus h, the distance is not going to be that much. For explanation I am saying. So theta, j of theta is here and j of theta plus h is here. Okay. So what is the derivative formula, or the formula we are trying to calculate slope? j of theta plus h minus j of theta divided by h, right? So this j of theta plus h is less number when compared to j of theta, so you are going to get a negative number here. So when you substitute into this formula, not this formula, this formula, what happens? Theta minus alpha into a negative number, which becomes theta plus alpha into the number, right? Whatever number, right? So it's going to add, so it's going to move in this direction. So any side you choose, it doesn't matter. Ultimately your algorithm will, the gradient descent algorithm will reach here, where the slope of the tangent for the cost function is 0. Okay, so that's another point we need to understand. And the third and most important point is, to converge faster, the gradient descent algorithm expects data in a similar scale. All columns should be in similar scale. Let us try to understand what is similar scale with an example, and then come back and look at the theory. If you take two columns, right, the column 1, the experience, right, ranging from 0.2 to 20, and the lines of code ranging from 0 to 12,659. Suppose that you are trying to draw a graph between these two, right? Suppose that you are trying to draw a graph between these two to understand the relationship, and you chose the scale as 12,659 on x-axis and y-axis, both 12,659. On x-axis we have taken experience, and y-axis lines of code, right? If you took like that, right, the lines of code, the experience is actually ranging from 0.2 to 20. If you look at the scale, right, it is 12,000. So maybe 500 here, 1000 here, 1500 and 2000, like that the scale is, right? So in 500 numbers here, where this 0.2 to 20 is going to be, it is almost close to that y-axis, right? So all the dots, where they will come? They'll come on y-axis. The pattern is not evident because the scales are different, and you have chosen the biggest scale on x and y-axis both, right? If you can do one thing, right, if you can bring both these data into similar scale, maybe between 0 and 1, right, then what happens? You can take 0 to 1 on both x-axis and y-axis, and then dots will come like that, and pattern will be evident, right? So how can we bring the data between 0 and 1? If you divide this data with maximum number, you can bring, and you divide this data also with the maximum number, you will get the data between 0 and 1. So that is what is called as divide by maximum scaling, we call it as. So we are scaling the data. Now x1 is equal to x1, the first record, divided by 20, x2 divided by 20, maximum number we have taken and divided. For the maximum number x, you will get 1. The minimum number 1 is going to be close to 0. Right? If 0 is there, 0 is also going to be there. So the range is going to, the scale is going to get between 0 and 1. Here also the scale is going to come between 0 and 1. So when all the columns are in similar scale, the cost function becomes a neat parabola. If all the x's are not on same scale, the parabola becomes like that, a slant one. When the parabola becomes slant, slopes at the tangents will be almost kind of 0. So when you are trying to calculate next theta, alpha is already small, and the slope is also small. The convergence becomes very difficult, and even for the 10,000 iterations also, there is no guarantee that the model will converge to the global minimum. So when you scale it and pass the data, the cost function will come like that, a neat, a steep convex function. When the cost function is convex, right, the convergence becomes faster, the step size becomes faster. So that is about the most important thing you should definitely remember to do scaling before you apply gradient descent algorithm. There are other scalings like standard scaling and min-max scaling. The standard scaling is nothing but the z-score calculation. x1 minus mu1 divided by sigma 1 is the standard scaling. x2 minus mu2 divided by sigma 2 is the standard scaling. Like if you have n number of columns, you will do z-scores for all those columns and take them as data. Then the model will work. The stochastic gradient descent algorithm will work. Min-max scaling. You subtract minimum of the column and divide by maximum minus minimum. That also gives you good scaled columns, and the gradient descent algorithm will converge faster. So that's about the gradient descent, theory on gradient descent and understanding. We need to understand these concepts well to play with the SGD regressor, not just to play with the SGD regressor. For doing deep learning also, these concepts are very important. So if you don't understand, go through them, once, twice, and try to understand it better. Thank you.